Hello. This is the third time I've recorded this lesson. The first time I forgot to mute myself during the video and was super echoey and annoying. And the second time I remembered to mute myself during the video, but then I didn't remember to unmute myself after the video was over. So, third time's the charm. Let's check this out. I'm going to mute myself now and then play the video.
Well, Jackie, I suppose we'd better get started. We've got a lot to cover today.
Hey, Sam, why'd they use this red paint? It's called the Golden Gate Bridge.
Actually, Jackie, it's not red. It's called International Orange, and the engineer picked this color because it was going to make a great postcard someday.
Really?
No, actually, he picked it for two reasons. It looks good with the scenery, and it's bright enough for ships and airplanes to see, even when it's foggy.
It does get kind of misty here.
Let's get to work.
What's the rush? I heard that as soon as this whole bridge gets painted, it's time to start all over again.
Well, you heard wrong. We never paint the entire bridge. We just keep up with the rust. The paint protects the steel from the salt in the air, which causes corrosion.
I never knew that. Let's get going. I've got tickets for tonight, and traffic's bumper to bumper already.
Okay, I unmuted myself. Yay! Small victories, bud. Let me tell you. Okay, here is your Jamboard. Notice the way cool pictures of the Golden Gate Bridge. Here's this one has a ship sailing underneath it. Look at all the sailors standing there. And this one is a schematic of it, and the bottom of the bay that the bridge stretches over. And then there they are. There's the Golden Gates. Okay, so we've been working on bridge breaking weights. We've been working on variables and equations and figuring out how to write equations or formulas. So now we're going to dive a little deeper into those things. Here's where they all come together. So it's often helpful to express functions with equations or formulas. The functions and their equations are called mathematical models of the relationships between variables. Equations tell you how to calculate the value of the dependent variable when you already know the value of the independent variable. In this investigation, you will develop skills in writing and using linear equations to model relationships between variables. Okay, organizing and displaying the data from experiments, such as the tests of bridge strength, helps you see patterns and make predictions. For linear data, you can usually find a graph and an equation to express the approximate relationship between the variables. The table and the graph below show the sample data from investigation 1. So we have the bridge thickness and the breaking weight, and then here's the graph of it. You can see that the points do not lie exactly on a line, but you can draw a line that is a good match for the data pattern. Drawing such a line gives you a model for the data. What line would you draw as a model for the data pattern? And how would you find an equation for this linear function? Okay. Good questions. You don't have to answer them just yet. They're more just to kind of get your mind thinking about what we'll be doing in this Jamboard. So the lines in figure 1 and 2 below represent two different equations or models for the data. The line in figure 1 connects the points at the left and right ends of the plot. The line in figure 2 passes among the points but doesn't hit any quite exactly. So answer these. These are not rhetorical questions. I do need you to answer these. Which of the two lines seem to fit the data better? Explain your choice. And can you sketch a line that is a better fit than these two? To find out how accurate each model is, you can calculate errors in the predictions made by the model. Those errors are the differences between the actual data and what each model predicts. Each such error is called a residual. Complete the tables below for figure 1 and figure 2 in order to find the residuals for each graph. So the way you do this, oh, I better get a pencil. The way you do this is you look at the graph. If the number of layers is 1, number of layers is 1. The breaking weight, the actual breaking weight is right here. This point is 12. And oh, I want red. I don't want black. And the actual breaking weight that was predicted, because the line went right through it, was 12. So the difference is the actual minus the predicted, or that's the residual. The difference is 0. For the second one, the actual breaking weight was 18, right there. And the predicted was right about there. Oh, I'm a little high. At about 22. So the residual is the actual minus the predicted. That difference would be -4. Okay. Try that 4 again. So you would actually, whoops, getting crazy here. You would actually find the residual. You would complete this table and then find the residual for each number of layers. And then you're going to do the same thing for figure 2. Because the model, the mathematical model, which is the line on the graph, is different in each one of these. So you're going to complete the tables for each of those. Then you answer these 4 questions. Okay, how would you describe the errors? Are they mostly higher? Is it mostly too high? Are they pretty much right on? Are they mostly too low? Sally has some ideas. How would you describe the errors of prediction or the residuals? Then go on to do this one. This is a paint crew. And you have to plot the given data on a graph. So here's your, I gave the wrong tool. Here's your given data. Here's your graph. So put your plots on there wherever the points are supposed to be. Draw a line to match the data pattern and find the equation of your line. The last thing you do is find the residuals for the model you developed for that line. And you're done. And that's it. Okay? So have fun with it. This is really cool stuff. It's so exciting. Okay. See you guys later. Bye.